Hi, my name is Coleman Fang, and this is a call for volunteers for a capstone project to develop a web-based tool for analyzing feedback circuits using signal flow graphs. Now, feedback is used in many analog circuits, but can be a challenge to analyze. So for this circuit from Cedra and Smith, example 11.3, you can see that you have a circuit. If you're trying to determine the loop gain in this solution, it requires you to take the circuit and to break it at some point in order to calculate the loop gain. In example 11.6, they take the same circuit and you can see them breaking it into modifying the circuit to create a feed-forward amplifier A and a feedback network B. So those examples kind of show the challenge of the traditional approach of analyzing feedback circuits, which is, first of all, identifying the topology of the circuit. In this case, it is a series shunt topology, and that's needed in order to break the circuit apart into its feed-forward amplifier A and its feedback network beta. This process, as shown in the examples, is prone to mistakes, and ideally there would be a system in place that would allow circuit designers to visualize and analyze feedback circuits without having to modify the circuits, break the loops, and would apply to circuits that don't necessarily follow this simple A-beta structure. In fact, this example has a nested feedback loop that is generated when we have source degeneration in Q1. So that would be the goal. And one of the ways to achieve that would be to look at the circuit and to go back to its equations to realize the fact that it is defined by a set of equations. So you can draw the small signal circuit and write out with nodal analysis the equations that govern this circuit. And that would be enough to describe the circuit. But in order to visualize the feedback, you can represent these circuits using a signal flow graph. And I won't get into the details right now, but these equations can be transferred to this signal flow graph. And in fact, you don't need to write down the equations. You can see it directly from the small signal circuit. You can generate a signal flow graph. There's a straightforward systematic process to derive the signal flow graph without writing any equations. Now, once you have a signal flow graph, then you have the possibility to work and analyze the signal flow graph in an interactive way. So you can look at its symbolic values, you can write in its numeric values, and then you can start to see relationships. So for instance, I can see that this branch is not significant because its value is 0.11, and the path from here to here, there's another path which is much stronger. 4 by 10 by minus 4 would be the equivalent of 160 milliamp per volt versus 0.11. So this is insignificant, and so we can actually just remove that branch in order to simplify the relationships. We can also do things such as eliminate paths by combining this path into here, so changing this value, so we can eliminate this path, and we can also collapse this feedback loop, and we can generate this circuit signal flow graph and combine all these terms together to generate a standard basic structure with the A, beta, and K. So the transfer function then is simply Ka over 1 minus A beta. Calculate, put in the values, and then you get the answer as in the textbook. But what's nice is you can go back and you can visualize the feedback here. As I said, there's the feedback, there's a nested feedback loop over here, as well as the larger feedback loop, loop 2, loop 1. And that's captured in the signal flow graph. So this method applies to any circuit, and it has no problem with multiple loops or nested loops. And you can see how we can simplify the signal flow graph through operations, and this is fundamentally different than the modifications of the original circuit in the traditional approach, because here the modifications are done on the signal flow graph. And the signal flow graph is basically an algebra, a visual algebra, and simplifying this would be akin to an algebra eliminating variables and dropping non-dominant terms. So we are not modifying the circuit, we're simply manipulating the equations in effect. And this gives us a lot more confidence in modifying the circuit, the signal flow graph, in order to get an answer. So this method has plenty of advantages, but the major disadvantage is how labor intensive it is to draw all these signal flow graphs and to continue to reiterate them. So the goal of this project is to create a system that would allow all these time-consuming steps of drawing the graph be performed automatically by computer rather than by hand. And ideally, you can see from the operations I've shown here, we'd like to be able to manipulate the signal flow graph by removing branches, collapsing branches, simplifying, and it would be nice to be able to show the signal flow graph with its symbolic values or its numeric values as a designer, so they can weigh the comparison of the relative strengths of paths. So the capstone project is prototype at this point is at a state where a user can go onto the system, they can import a SPICE netlist, and the system will then generate a signal flow graph like this, and the signal flow graph allows you to look at the numeric values, but you can also switch to the symbolic values. So, and you can go back and forth, and it'll also allow you to look at dominant paths, identify dominant paths and non-dominant paths, so you can select which ones to simplify. Throughout this process, the system can generate the transfer function if you pick a particular input and output. It'll also calculate the transfer function, the loop gain, rational expression for the loop gain, and it will generate the Bode plot for the transfer function or the loop gain. And the loop gain is key to understanding the stability of the system through looking at its phase margin primarily. So The team has taken the project to a point where we could use some testers to test out the system and give us feedback. If you are interested, then we'll probably run a session next semester at a convenient time, probably reading week. It'll take a couple hours as we guide you how to use the system and try it out with a few feedback circuits and then get your comments. We are hoping to create a system, a tool that will be interactive and help students and analog designers in industry better analyze feedback circuits. Thank you for your support, and if you're interested, then please send me an email. Thank you.